All right. I'm going to turn off the light so you guys can see. All right, so Lewis structures. Lewis structures are going to be these fun little drawings. So we have to start with the Lewis structures before we can move on to worrying about shapes and things like that. So you've got to be able to draw these well. And so you guys being advanced chemistry, I am going to force you guys to use a method known as needed available shared. So it's NAS. So we'll get to that at the very end, and we'll see how much time we have for practice. Okay? All right. So Lewis structures, electron dot notation for your covalent compounds or molecules. Molecules is probably the better word to use. All right, it's molecular. Oh, wow. I'm going to zoom in so you guys can actually see. There you guys go. All right. So there are 3 parts. First, we have our atomic symbols. They represent the elements. Who would have known? We have our dot pairs or dashes between them, which are going to show our bonds, right? So they represent the bonded electron pairs. I totally ran out of room right there, sorry. Bonded electron pairs. And in our final answer, we will use a line or a dash to represent the shared pair of electrons. So bonded, shared, same thing, all right? All right, cool. So then, it's really important to remember this thing because you're going to be counting in a second when we start drawing these. Each dash or each line is going to represent how many electrons do you think? How many electrons are getting bonded? 2, exactly. So make sure you remember each line will represent 2 electrons. If it will help you to draw or dots at the end of these lines, that's fine, okay, until you get used to it. All right, cool. So dots are attached to only, dots that are attached to only one of your elements, or atomic symbol, will represent your unshared electrons. So remember for our electron dot notation, like for something like, let's just say oxygen, right? Sorry, 1, 2, 3, 4, 5, 6. You have these things. So you do have 2 dots, right? So 2 electrons. These are not being shared. The only sharing places that you have is kind of like when we were doing our ionic stuff. We put arrows to the ones that were by themselves, right? Those are the only areas that it can bond at. Okay? So when we're talking about dots that are only attached to one of these, and they're in a pair, that does not mean it's a bond. So just remember that, okay? You do have to draw out the dots to show that they're a lone pair. So the unshared pair is called the lone pair. And they are not involved in bonding. So they only belong to one atom. And the reason why that statement right there is important is because you are going to have to check yourself. You're going to have to check to make sure everybody got their octet satisfied. Okay? You got to check to make sure everybody has 8. Okay? All right. And remember the lines represent 2. Even if it's attached to another element, it's going to represent 2 electrons. Okay. So, types of covalent bonds. So this part is why I'm going to be forcing you guys to use NAS. Okay, I'm going to have you guys do that so that you see, oh, we're supposed to have 3 bonds, but I only have 2 elements, and that'll tell you have to bond them together with a triple bond. And that's why I'm going to teach it to you guys that way, okay? Because you guys being advanced, you guys will get to see expanded octets and things like that, okay? So your types of covalent bonds, they're pretty simple. A single bond is only going to have 1 pair of electrons shared. I don't know why we have to write that in. Sorry. Between the atoms. It's represented by 1 line. So, for example, if we had diatomic hydrogen, we would have it like that. Now, question. Do I need to put any lone pair of electrons around these? Any other dots around those hydrogens? No, because each hydrogen only had 1 spot to bond, right? Remember that. Okay. Double bond is the sharing of two pairs of electrons, and we represent it with two lines. So an example of that would be double oxygen. So remember, oxygen, we just drew it up here, has two spots to bond, right? That means that it can form a double bond when it's diatomic. So we're going to put oxygen with another oxygen, and we're going to end up seeing that we got it. So that represents 4 electrons. How many do each of them have to have? Oh gosh. How many does everything need to have? 8, right? So if I only have 4, 1, 2, 3, 4, how many more do I have to put on this oxygen? 4. So 1, 2, 3, 4. There's my lone pairs, okay? And then this oxygen, now we're going to cover this one, right? 1, 2, 3, 4, 5, 6, 7, 8. See how that works? Okay? All right. So your double bonds will be shared between 2 pairs of electrons. So your most common ones, so the ones to look out for to do this, most likely with, is going to be oxygen, sulfur, and carbon. If you notice, oxygen and sulfur are both in group 16. So they both have your electron dot notations of this. So it's pretty obvious. Carbon, not as obvious, but it is a common one to form these single, double, triple bonds. Okay? All right. Because carbon has 4 places that it can go. So it can go double, double on both sides of it. Okay? All right. So a triple bond. A triple bond is the sharing of 3 pairs of electrons represented by 4 dashes. I'm just kidding, don't write that. 3 dashes. I just want to see if you guys are listening. But anyway, it's 3 dashes, right? So any guesses of what is the most common element that will bond in with a triple bond? Think about it. You might have to look at a periodic table. I haven't heard it yet. Did you say? Well, okay. Well, it's going to be part of that 7, yeah. What did you say? Wait, which one did you say? Yes, but you're absolutely correct. Okay. So she said nitrogen. Let's look at why. Nitrogen has how many valence electrons? 5. So it has 1, 2, 3, 4, 5. How many spots can it bond on? How many spots allow bonds? Yeah, 3. So he can bond up all 3 of them. All right. So nitrogen is a very, very, very common one. So nitrogen. And then that also holds true for everybody in group 15. So we're not going to write that. We're going to write carbon. Because once again, carbon is your friendly element. Your friendly neighborhood element. So it bonds however it wants to. Everybody bonds to it. All right, so nitrogen. So a triple bond would then look like, we're going to draw it down here so it's a little bit prettier. Just did a lowercase. There we go. And our lone pairs are going to swing to the outside. So something that we talked about in first period that I wanted to emphasize with you guys as well. So you notice that I put the lone pairs over here and not at the top. You guys see that? Okay. What are electrons probably doing if there's more electrons around it? Repelling. Yeah. So they're still all negative things. What you guys are going to see, and hopefully on their lab, I think if I don't start you guys on it tomorrow, I'm going to start you guys on it Friday. But what you're going to see, it's a cool computer simulation, is that your lone pairs repel. They repel like crazy, and they're going to go as far away from any of the bonds as possible. That's why up here you saw that I swung those guys around too. You guys saw that I put them at angles, right? So it's because those lone pairs are going to definitely be repelling. All right. So next, now we're going to start the process of actually drawing these things, okay? So remember these basics that I just gave you up here. We're not going to write the steps to drawing yet. We got to first come up with probably the most important and challenging thing, and that is determining who goes in the middle. Yay, because you get these like compounds like this, and you're like, I don't know which one will go in the middle. Okay? So often it would be the unique atom. Do we know what unique means? Unique means just different. Okay? You're good. Never mind. It's a dad joke. I'll just leave it alone. All right. So often the least electronegative element. So think about that sentence. The least electronegative element. Question, are we dealing with metals anymore? Like any of these guys down here? Do they even exist in our covalent drawings? No, right? The minute you get a metal, you're doing the arrow thing again, okay? So you are limited to over here. We're looking for least electronegative. So we are really getting as close as possible to our metalloids line, okay? So get as close as possible to the metalloids line. Those guys will have more spots to bond on if you think about it. They have more than one electron that can get bonded, okay? All right. If carbon is present, remember I said he was the friendliest element there, okay? It's going to be in the middle. So the minute you see carbon, throw them in the middle. All right, number 4. Number 4, we kind of expanded this sentence in first period, so we're going to put what's supposed to be there, which is hydrogen. Hydrogen cannot be central because hydrogen's dot notation looks like that. Can it bond with anything but one thing? No, it's one thing and that's it. It like bonds and then it's done, right? So it can't be in the center of everything. It can only be with one other thing. Does that make sense? Unless it's on the outside. The other ones that can only most likely be on the outside is what group on our periodic table? Think about it. What other group on your periodic table can only bond with one thing? So again, think about dot notations. Which ones only have one single dot? No metals. Leave those guys alone. You're not on that side of the periodic table. Other side. Come on, you guys got this. Let's go. Remember, when you draw your dot notation, you go 1, 2, 3, 4, 5. That bonds 3 places. 6, 2 places. 7. You can't go 8. 8 is up here, right? But 7, right? 7 will give you one spot to bond. Group 17. All right, so try to put group 17s tend to be on the outside. All right. So usually put your group 17. So fluorine, the most electronegative element. Think about it. Those guys are the most electronegative as well. Okay. So, got it. Cool. So you're going to be checking for octets. Now, when I say octet, we do know not everybody gets 8. For example, who does not get 8 for sure? That is written right there. Hydrogen, right? Exactly. So we have some exceptions. All right. So you have to make sure that each element has the right number of valence electrons. So all should have 8. So when in doubt, it's 8. Okay. But we do have these 4 exceptions, and you guys being advanced, we do make you guys know these, okay? So we're probably not going to provide them to you unless I'm feeling super, 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 super nice, all right? So your exceptions are how many? I'm going to rewrite them so they're a little bit bigger. That's cool. Yeah, I'm just going to rewrite them so they're bigger. Hydrogen. How many does hydrogen need to have? 2, exactly. It has 1 spot. It can only hold up to 2. Okay, beryllium, that should already start bothering you because what side of the periodic table is that on? It's the metals, yeah, exactly. But you're going to be covalently bonding that one. It has to do with being on that second energy level, okay? Everything in second energy level gets funny. All right, so beryllium, what do you think its number is? 4, why? You don't know? Good, yeah. So beryllium, if you think about it, you don't have to draw this, but if you put beryllium, you have 1, 2, it has to go 1, 2, right? And this would actually be spread out. So it can only bond on this side and that side. All right. You won't see it do doubles. All right, and then we have boron. How many do you think that one's going to have, Max? 6, exactly. And I hate adding this one to the list, and I usually refuse to, and I take this one off if I ever see it. But just in case you do see it, covalently bonded to something, what do you think its number is? It's right underneath boron. 6. It's also going to be 6, yeah. Trust me, it's annoying. But just in case you see it, because it's probably going to show up on one of our old worksheets that we use, that's what it is. All right, so those are the 4 exceptions to this, okay? You don't have 8 for those. All right.